Yeah, hi everybody. And the unit we're going to be doing, this is effectively what you're going to be missing on Wednesday. I'm going to probably review some of it with you. I use both, I'll be using both this PowerPoint, which as you can see is the whole chapter 14, which I loaded. And I'll be loading one from the Marib series also onto your Blackboard, but that'll probably get done perhaps Monday or perhaps when I return. But all that aside, this is what we're working on. It's the unit about the blood. And neither one of these is bad. I think the two of them together make it pretty complete when we do both of them together. So that's kind of why I'm approaching it this way as opposed to just using one home. So here we go. And they all say the same thing, just in a little different pattern. So we'll emphasize some things, we'll take away some things. I think there's a lot of important stuff in the blood, particularly so. It's a unit that I enjoy teaching. Uh, I don't know how you're going to approach it in lab, particularly. It's really more of a physiological one. I mean, blood typing and things like that. Unfortunately, you won't be. You may have done this in high school, sticking yourself and testing to see if A, O, etc. I do not know that that is part of the curriculum that is approved for the AP2 labs, and I do not think it is. And that would certainly be up to Dr. Robbins in any event. But all that aside, and he and I can always discuss it if that they want to add that to the curriculum. But I don't know if it's on there for this term. You'll have to ask him. Nevertheless, you'll be looking at blood cells and things like that all the time. That's really good stuff. The blood is a connective tissue. That may surprise you because we think tissue, we think solid, but tissue just means that it has cells, and Lord knows this has red blood cells, white blood cells, and cell fragments called platelets, and it has a ground substance that happens to be liquid, we call it plasma, and it has fibers. Well, blood's a liquid, where are all the fibers? The fibers are called fibrinogen, and fibrinogen are produced as one of the proteins that are produced within this particular connective tissue, except the fibrinogen happens to be soluble, which means it's dissolved. The magic of clotting your blood is effectively all the steps for blood clotting, and there's two different pathways that we'll get to, but probably not today or in this sequence, are really the bunch of steps that are steps of a bunch of enzymes that catalyze, in other words, from one step to another step to another step, and change eventually to the point where they reach a chemical that's going to change fibrinogen into fibrin, which is insoluble. They take it from its precursor form that's dissolved in the plasma, and it comes out, and for all the world, it forms a fishnet that traps red blood cells and firms them up, and it's what we call clotting. It's a fascinating thing. There's two different pathways you need to be familiar with. So there's a lot in this particular physiological chapter. And that's why I did not certainly want to put it in, given how much time we had to prepare for me to get this first exam in. So we had plenty of content as it was anyway. And what does it do? Transports vital substances. The homeostasis is really a part of it. Okay. So, I mean, think of heating and cooling, redirecting blood to certain areas to warm them or take them away. We'll redirect blood when it's cold outside to our internal. That's why our fingers and toes get so cold. Okay, by the same time, we'll direct blood when it's warmer more towards the skin, and that kind of facilitates the onset of perspiration and generating heat that's kind of radiating externally along with perspiration. And it's a cooling process. And it's very, very stable. We have a lot of mechanisms that are in there. And the single most, and maybe let me talk about this for all of you in AP1, the single most important buffer, an agent that maintains our bloodstream in and around a constant pH of approximately 7.4 plus or minus 0.05, so 7.35 to 7.45, and the blood stays remarkably there because so many of the things that govern the way our body does work are governed by pH. So the amount of blood, certainly it varies, okay? And there are some changes in concentration, and Fatty tissue plays a role. That may limit things, that may increase things. There's all sorts of things that play a role with regard to this without going too crazy over it. You see it's about 8% of body weight. And you can see the difference that I started to comment on a little bit when we're talking about endocrine, when we're talking about women versus men. Women, for a goodly portion of their lives, menstruate. Women do not make testosterone, which also augments the amount of red blood cells we have. So you can see that that's where the difference is. Very, very much so. Size may be playing, but proportionally speaking, that the major differences, particularly vis-a-vis red blood cell production, are the testosterone that men produce constantly versus the androgens in a limited amount in menstruation during childbearing years. Voila. And size, obviously. See, we don't even call them cells because only one of them is a cell. And it's not the most abundant. It's not even the second most abundant entity. It's the least abundant. We got the least of them. Those are white blood cells. Those are true cells because they have a nucleus and other organelles. Platelets, which are many times more numerous rather than white blood cells, are just fragments of cell and cytoplasm with an abundance of granules. Those are the clotting factors, as you will see. And then the red blood cells, they were a traditional cell, but as they mature, they effectively shed their organelles and eventually the nucleus. And then they become really this, what we call a formed element that's uniquely shaped. And I commented on it earlier, an earlier presentation, we talked about the eye with double concave, that which the eye, which the lens is not. But I commented on that being an increased amount of surface area, which is available for oxygen carrying capability. And we're going to see that again when we start looking at biconcave discs. So it's already very, very interesting stuff. And this is really the basics that I'm going over now. The clotting aspect, really, when we start to look at the implications of blood typing, the implications of transfusions, changes that were made by the blood bank. I have an abundance of information to share with you about that because of my own personal difficulties, which I'll reiterate in class. I've had entirely too many transfusions in my life, and they were pretty much all concentrated in about an 18 to 24 month span. Moving on. Pretty good chart. This gives you an idea. And the number here, the 45 to 55 that you can see here, has to do with what percentage is formed elements and what percentage is plasma. It's got the most famous name. And it's such an important measure that we talk about it all the time. Clinically, it's called the hematocrit. Hematocrit. And I have a handout that I'll put on Blackboard, obviously, rather than give you the paper handout. And hematocrit is really the percentage by volume of what are formed elements and what is plasma, which is the liquid component with all the stuff dissolved in the liquid. And then the average norm is about 45%. It's interesting. That's just a percentage. But we can approximate hemoglobin, the other famous measure. Okay, I talked about it a little bit in class, sort of the definition of different kinds of anemia. One that I have has to do with from previous surgical procedures and the fact that I just don't make quite as many red blood cells as I used to. Okay. And you can approximate that measure called hemoglobin by dividing that number, whether it's 45, 48, 50, 36, whatever it is, by 3. So if mine was, let's say, argument's sake, 40, my hemoglobin would be around approximately 13.3. So we look at hemoglobin and hematocrit as really important measures to give us a snapshot into whether someone is anemic, borderline anemic. You're going to see maybe they have too many red cells. We call them poly for many, psi for cell, themic means in the bloodstream, polycythemia. We look at all those factors, and we'll take a look at it and how they derive it, and something we do in the lab. I do not know whether you do it in your lab, but we can. We don't have the best technology for it, but we have what's called a centrifuge, as you will see shortly, and effectively we spin the blood down. Which, by the way, everybody, this is exactly what the blood bank does, because if you're unfamiliar with transfusions, You rarely use a whole blood transfusion. All of the components of the blood, the platelets, the white cells, the plasma, the red cells, all have uses. And frequently it's easier to give those components and then add liquid or isotonic liquid or saline or whatever to compensate for the remaining volume. So a lot of times you're looking at different uses. How do we separate them? The most common method that we use in the laboratory for separating things, and it's been around forever, is called centrifugation. And basically, you're spinning it. You see what a centrifuge is, just go on a ride at Kennywood or any amusement park that goes in a circle. And if you're sitting on the outside, or if you're sitting on the inside, you're getting pushed over, slid over to the person on the outside. It is not fun. It goes very fast, but effectively that's what centrifuge is. And what it does, when it's spinning, the heavier portions of all these materials go to the bottom of the tube. You could do this over time if you just let the tube sit and allow it to settle naturally. And there's reasons we do that as well, by the way. But by and large, okay, you're going to see that centrifugation is the way that the blood bank is able to rapidly separate these and effectively siphon off the parts they need and preserve them. So look what you have in those formed elements, that 45%. You have 95+% red cells, nearly all the rest platelets, and a scant 0.1%. If you want to think of that, it's almost like and this is what I use, for every white blood cell, there's about 1,000 red blood cells. So when you start to look at these under the microscope, if you haven't already done so, you see a sea of red cells, you see lots of platelet fragments, and occasionally you see a white cell. Fortunately, they're very distinctive, and it's easy to tell which is which, and that's part of what we do in this chapter. And you're going to see, and they've done this for a particular reason, the way they have set this up, because it has to do with cell lines. And you're going to see that we're going to learn about the most abundant, I'm using that word a lot in this particular presentation. The one we got the most of, called neutrophils, because they stay neutrally. We're going to get back to all that. The ones that we have the next, lymphocytes. Then after that, monocytes, those become macrophages. Something called eosinophils, because eosin is a chemical that stains red when we use it. And you're going to see there's a lot of little red granules, and basophils, which happen to have a very blue or basic staining granule. Just so happens that's there. So you're going to go into all those cells and their importance. And it's really important to get a background of them now, because these are the cells, the linchpins of your immune system. And they play a very pivotal role in a lot of the way your body responds to infection, inflammation, problems, invasion, damage, etc. Plasma. Anything that's not a formed element, okay, is effectively dissolved in plasma. Plasma is a liquid, okay? You should be able to see through it. It's a solution. So you have a variety of charged particles, sodium, potassium, chloride, all those guys, calcium, mostly water, as you can see. So all of these, between charged particles, waste products, nutrients, even gases count, okay? There's something dissolved in there, because gases have a certain concentration when they're dissolved in water, or in this case in plasma or a water vehicle, vitamins and hormones, chemicals. So 92% water, 7% dissolved proteins, and the proteins are big time important. And we go over all this. The three basic categories of proteins are albumins, which are by far and away the most, about 60% are albumins. Globulins, 36% or so are globulins. Those 36% include immunoglobulins, which you and I sort of generically refer to as antibodies, that obviously play a pivotal role in our immune system, and globulins do other things as well. And then lastly, the one I talked about 4% are fibrinogen. And again, I'm going to go over all the roles and usages of these, and all the things that they do and why they're important. So what do we do all the time in the lab? We draw bloods. And what I do as part of this is, I don't have to worry about HIPAA. I'm going to show you mine. my blood test, which I've had a lot of, and I just get my UPMC app up and show you the screen with, well, let's say, my most recent couple of sets of blood tests, which would typically include a CBC, complete blood count, a differential, which we'll get to and what that is, and what we call a BMP, basic metabolic panel. Things like glucose, calcium, sodium, potassium, that kind of stuff that are on there. So plasma, again, everything is dissolved in there. So it's a solution. It's clear. That makes it a solution. Straw colored. It does have that sort of a yellowish tinge, let's say. And it's the matrix of the blood, 55%. And you're going to see that it goes to the top because the formed elements, since they're formed, they are heavier because they're not all liquid. They have a lot more solid, many solid components. Typically, the range depends on the author. This author, 35 to 46 in females, 40 to 54 in males. So in males, it's not where it may not be that common, but you're not you're not throwing up a flare of problems if it happens to be 54%. That would be hemoglobin of roughly 18. So you can see the range, 13.3 to 18. This is this author's range. Here, this is under 12 to slightly more than 15. Typical ranges I've seen 12 to 15 and 14 to 17 are average. If you look at all and I probably have used in my teaching career, I don't know, 20 different anatomy and physiology books. And that percentage, based on volume, is called hematocrit. So you can see, and white blood cells and platelets are, why is it just only 1% of the volume? Well, there's not a whole lot of white blood cells, and platelets are fragments. They're very tiny. And you're going to see that they're lighter than red cells, but heavier than plasma. So they form in the middle, and that middle area is referred to as a buffy coat, meaning it has a certain color that's a buff or an off-white kind of color. It's like a film, if you can imagine it. When we do it in our lab, we don't typically see it because we're not using a very large volume. We're using tiny test tubes. And so here it is. If you can see it from this illustration, and here you are typically doing a blood draw. You can see the tourniquets there. You can see the tube. These are called vacutainers. They're sterile on the inside. There's a vacuum to help pull things in. And here they are spinning it down. That's the centrifuge. And so when they spin down a tube, this is an interesting tube to discuss. It's called blue top tube. Pardon me. I'll have a drink coming in a second as soon as I cough. All right. Blue top tube is something, interestingly, I don't know why I picked it for this unit, but when you're measuring someone who is on blood thinners, you typically use a blue top tube. When it has certain chemicals in that effectively don't permit the blood to clot, so you can evaluate the levels of certain clotting factors that are, not clotting factors, of clotting chemicals that are in there. Not something we go into in this course. That's more of a lab course or maybe a more advanced course. And here you can see a red top tube. Red top tubes don't have any in them. That's typically used for the chem profiles. So they're empty, but there's different ways why we have material in there and things like that. They're all different. I don't understand that well, Michael. I don't do the lab stuff. I don't teach a lab tech or a lab technology course, etc. And this is what, you've seen better smears than that, but white cells, platelets, and here you can see it. So effectively, we just measure this because effectively this is a cylinder. So length equals volume. Since the diameter is the same, length equals volume. So if this is an inch, and this is slightly more as it is than half an inch and slightly less than half an inch, you just do the math and you get the number. Interesting they put this here. This is something I bet you're thinking about as you're listening to this or as we go over the slides. And I'll buzz through these on the other slide set, is universal precautions. Okay. And these are things, and it's not just healthcare workers. I think that's painting with too small a brush, as it were. But it's about transmission of bloodborne infectious pathogens in the workplace or in whatever you're doing. We have developed a concern over this. We're probably overly concerned, but there's a lot of we don't know. When HIV first came out and we heard about AIDS, oh my God, if somebody had a drop of blood, everybody they went into panic. Okay. And frankly, most of the people who are talking to you aren't aware of this. They weren't necessarily around, or they were babies when this was all going on. And they don't understand what it was like necessarily when we were there at the onset. But without going into all of that stuff, understand, yes, the principal thing, and this again is pretty limited. We're using it, sure, we're concerned about HIV, but you don't routinely test for that. That's not something you order routinely, and there's all sorts of legal implications from a provider standpoint, from a doctor or nurse practitioner. Hep B virus used to be a big concern, but we have the immunization now. Hep C is certainly a big concern. Okay, and there's a whole lot of other things that we worry about with regard to this. There's other types of things, and potentially could be bloodborne, you have to be concerned about, and particularly. And this is why we're so concerned when someone has an open wound or has an exposed area. Why we wear eye protection frequently to do that, because those membranes of your eyes don't have any protection. You get it in there, it can suck it right up. You have more protection in your nose and your mouth than you do there. Just little things I'm throwing out there. So universal means, yeah, if you don't know, you can't tell. I mean, and you heard me, you didn't learn in the class where I talked about this, or I haven't blabbed about it before, which is unusual for me. There goes my voice again. At the end of the day, I'm doing this right before the Super Bowl. We didn't have to wear all that universal precautions weren't standardized until about 1994. Somebody came with you slapped your hand over it. We had our hands in open wounds. This is 1977, 79, and we were in Philadelphia, and AIDS was everywhere, though nobody knew its name, but it was all over. Okay, so as you can see, a lot of times this has to do with injections. There's problems with shared needles and needle exchange programs, and a certain degree of controversy with them. Don't get into it, but understand it's very easy. And people don't know what they're doing with these things. And we're talking about intravenous drug users and skin poppers, which is a different kind of way that these are used. And I have a lot of information if you're interested in that. And so personal protective equipment, which you're going to get chapter and verse on if you're nursing. Sharps containers, same deal. Fume hoods, not something you use routinely, you do in the laboratory. And other than keeping your hands and skin intact and using the personal equipment, hand washing. And so it all starts with this. It's called hematopoiesis. So it's just basically origin of the formed elements. Not really. I can't give you the truth. How shall I say it? Really all the word roots, how they come together, but they come from a stem cell. And there's a lot of stem cells in connective tissue. This is the one associated with bone marrow. It's got a fancy name you don't have to know, called hemocytoblasts. And they give rise to two different lines, effectively, that go on and give rise to even more specific cells. But their stem, there's two lines. The lymphoid lines, which is lymphocytes and monocytes, and the myeloid lines, which is everything else, red cells, all the other white cells, platelets, etc. And you're going to see it. And they named it because of the lymphocytes, I think, more than anything else. But the reality is, what these cells have in common is when they stain, they have visible staining granules. Lymphocytes and monocytes have granules in them. They just don't stain visibly. We know that there are chemicals in them, maybe electron microscopically they're revealed. So we call these, and maybe it's a misnomer, we call particularly the white blood cells in this line granulocytes, because you can see the granules, and we call these A for without, granulocytes, all one word. Voila. Here's the myeloid line. We'll get, and I'll have a better detail to show you. This is called an erythroblast, red blast, the megakaryocyte. So this makes more and more stem cells, and I'll show you on a different slide series the different ways it progresses, and finally it gets all the way down to the erythrocyte. We'll talk about what a reticulocyte is. It's important. And here you have this megakaryoblast. these little fragments that you can see here, so the cell doesn't divide, it replicates. And these little fragments kind of just pinch off. It's almost as though you had a strainer. This big blob of stuff in the strainer, and you started pushing it through, and little bits and pieces got pushed through. That's really the better analogy for these platelets. They're very tiny. And here you can see the myeloblast. This forms the three major types of granule. You can see the little dots. Those are reflecting granules. Neutrophils, eosinophils, and basophils. I have a lot of info on these. And here's the lymph line. Less monocytes, which become macrophages, and you're going to see T cells and B cells, lymphocytes, and something called a plasma cell, which we'll get to. And a lot of that's immune system. We reiterate a lot of the white blood cells in the immune system because they're the linchpin organization. Just to understand a little bit about where this comes from you can see it is a limited line, but you're going to see in this PowerPoint, just to get a little ahead of ourselves, you've heard somebody having leukemia. Leukemia is relatively, I hate to say common, but it's a blood cancer. It's a bone marrow cancer. And it'll either say lymphocytic or myelogenous. It's either in this line or it's in that line. Lymphocytic involves these cells and myeloid line. You can see all of these cells. Geez, they look. It's one nucleus, but you can see it's kind of pinched and it appears like it's fragmented. And this nucleus is all one. So when you hear the term mononucleosis, it's not just monocytes. These are called mononuclear forms. It affects this cell line. And mononucleosis is something you all know somebody who has mono, and you will if you don't by the end of the term. So here are the red blood cells, biconcave disc, about a third hemoglobin. In a typical red blood cell, there's about 250 million molecules of hemoglobin. And since each one has 4 places to carry an oxygen, you can carry about 1 billion molecules of oxygen for every, are you ready? For every red blood cell you have. And you've got a bunch, as you will see. So we call that oxyhemoglobin. And when it loses a percentage of this oxygen, it's not the whole thing. It's like magically all the oxygen went away. That confuses students. When your blood gives up oxygen from an artery and then goes into a vein, it typically loses about a quarter of its oxygen. Because if that was the case, it lost it all. When someone had a heart attack and their heart stopped, they would immediately die. And they don't, because there's still oxygen that's available to be given off. And the interesting thing about it is when we talk about its maturation cycle is that the organelles disappear, including mitochondria and nuclei. They don't need them. They can't divide. They have a lifespan, depending, I don't know what this author says, typically between 90 and 120 days. Typical average is about 100. So you get an idea how long that when somebody donates blood, probably, I don't know what I was told once it's about 2 months. They'll keep it because then you're going to have some of the blood you collected is just no longer functional. And yeah, there are ways they can produce certain amount of energy, but it really rarely doesn't. You see, it can, but it typically doesn't. That's not really its job. Classic example, great micrograph, all surface area. So you have all of that surface area. This is all the hemoglobin area. They're not big at all. This is a micrometer. So let's take a thing. E. coli is probably, maybe you could put a chain of about somewhere between 7, 10, 15 E. coli across. You know what you're looking with under your microscope. Probably, 10, a dozen staphylococci across, maybe a little less, maybe a little bit more. Depends on, there are so many different species. And so here's to give you an idea. If you want to do the math, you can. So let's say the typical thing, just for argument's sake, say 5 million microliters. That's a millionth of a liter. So a liter is roughly a quart. You got about 5 of those quarts. So, you can start doing the math. You have 5 million of these times a million times 5. 5 million times a million times 5. That's all. and your blood at any one time, constantly being recycled. I mean, so you have 5 million, and this is another million. So now you got whatever that comes to. It boggles the mind how many there are there. I should try to do the math and with scientific notation and see what we can come up with on that. Maybe we'll do that in class. So you can see we're roughly about the same, not a dramatic difference. And so we look at these, and really the disease that we talk about the most with regard to red blood cells are anemia. There's lots of different kinds of anemia, from blood loss, from diseases. Most of them come from blood loss. Sometimes it's dietary, sometimes inability to utilize iron. It can be vitamin deficiencies, and it's all about this because red blood cells have one job: carry oxygen. That's their job. So forming them in the bone marrow, when the oxygen levels go low, your kidneys sense this. We talked about this. The kidneys, and to a lesser extent, the liver releases erythropoietin, and that stimulates red blood cell production. Negative feedback. Once the oxygen levels are back where they are, or if the oxygen levels are too high, they'll just stop making it for a while. Because again, red blood cells have a lifespan. X amount of time, and some of those red blood cells will be no longer functional. They'll be effectively, typically your spleen and even your liver will gobble them up, break them down, reuse the components, and make more. They just won't make more at a very fast rate. So it doesn't take much. And like I said, this is one of those, erythropoietin is something that was one of the early by my standards, in the sense that if insulin came out in 77, we're in the mid 90s and we're starting to see erythropoietin being made in the lab. And so it goes through a varieties, and the one that's most interesting is a reticulocyte. I have to do that in lecture, and I will. Average lifespan 120 days. So when you take blood out of somebody, you're going to donate blood drive. If that's the average, you have to figure that whatever there'd be a formula for how many are how old at any one given time. And that's where that 2 months roughly comes from. You've got to have B12, that's part of maturity. You got to have folic acid, that's part of maturity. Because without those, you can't make the DNA that we have to have. Okay? Necessary for the growth and division of all cells. Okay? And so they play a role in other cells, but particularly so in red blood cells. And iron, because without iron, you don't have enough hemoglobin. The problem most often when people have anemia, which technically would mean a lack of cells in the blood, we're talking about red blood cells. We'd specify if it was white blood cells, they call it a leukocytopenia, okay, or insufficient platelets. But when you hear the term anemia from a hospital sense, from a medical sense, red blood cells, okay. And so that's when you talk about anemia, as you can see the definition here. So it's even though there's nuances to this, for you, that's the word that's important. I'm just showing it to you, how it happens. So you have anything, whether it's the liver, and it's mostly the kidney, the liver has a much lesser role, okay, that will implicate it. Okay, so if it's low, the kidney will act more, it gets to the bone marrow, make more feedback, who cares? We'll get to B12. And it also involves something in your stomach. Vitamin B12 is something that doesn't work orally normally. It requires something else. So you had just B12 and you couldn't make this stuff, and this happens to people. It's called intrinsic factor. There's special cells we'll get to in the digestive system that make something called intrinsic factor. They allow B12 that you get in your diet from food you consume or a vitamin supplement to be absorbed in your small intestine. If you don't have the intrinsic factor, and there's a lot of reasons that can happen, it really impacts, and I'll go over the different kinds of anemia when we get there. That's that. It's got a fancy name. Okay? It's called pernicious. Where the name derived, Pernicious, anemia. Interestingly, folic acid is in the same category. Folic acid absorbs a little bit better, and you're going to see a lot. And you just go anywhere. If you have multivitamins you take, look at them, see on the back of the bottle, or you can go anywhere. If it's a Centrum, it's one a day, whoever. If it's any vitamin maker today, if they're generic vitamins you get from any place that you shop, They're going to give you a list. This way with any food you consume, and you're going to see. And folic acid is one of the things we have to acquire by diet, as is vitamin B12. There's a little good news about the B12. Folic acid doesn't require the intrinsic factor. B12 can be taken by injections, even nasal gels could be absorbed directly into the bloodstream. So there's different ways to get B12 in. The only note that I would make about B12 that's interesting, as an aside, because I have a couple of vegans in my family, my extended family, my wife's kids. B12 usually comes from animal sources. I mean, you can go online and they'll have vegan B12. How they source it, I do not know. From on Amazon, where it'll be from the non-animal sources, and serious vegans, they take that seriously. We get iron from a lot of different stuff. Some people have difficulty using it. And these are all the anemias. I'm going to skip that for now, but just an idea. You can lose it by bleeding. There are infections, even transfusion incompatibility, something we'll talk about with transfusion. Hemolytic means it tears apart the red cells. So think of a mismatched transfusion. That's one of the big problems with it. Hemorrhage, self-explanatory. Hemorrhage doesn't mean bleeding outside. Hemorrhage means bleeding inside as well. That was my problem. Here's a pernicious anemia, okay, with B12. And now, when they talk about aplastic, it means all cell lines are affected. And the problem is you have a lot of red cells, you have compared to a few white cells, and people succumb to infections. Unfortunately, it's difficult because if people are getting radiation treatment, cancer chemotherapy, even caused by cancers, viruses, certain antibiotics, certain poisons, they all can damage the bone marrow. Bone marrow is very sensitive tissue. And I mean, we really see a lot of problems with it. There's some, I talk about antibiotics. I'll probably mention one in passing about that, called chloromycetin or chloramphenicol, that caused aplastic anemia. Not all the time, but in a few. And here you can see some other ones: iron deficiency, iron problems, menstruation, and what I had, a persistent bleeding ulcer. And now you get to the ones that are genetically based, sickle cell, which we'll talk about, and there are different kinds of thalassemias that are there. And so if you take genetics, and you probably learn thalassemia is more common than you think, but they're not as severe as sickle cell. Here's said cells sickling. When oxygen concentrations are low, going up at altitude, prolonged exercise, things begin to sickle, and unfortunately, sickle cells clump up, and when they clump, red cells clump together, they clot. More on that down the road. Sickle cell is interesting. It's we call a point mutation, an isolated mutation, called a fancy names we're going to learn about in micro. Many of you call it missense mutation. Abnormal structure, it sickles, blocks blood vessels, particularly when there's not enough oxygen available, and particularly going into organs, and all of a sudden they don't have enough. And the greater the amount of oxygen deficiency, the quicker it happens. And really any anemias, you're going to see the big single most important thing is fatigue. I will talk about that down the road. And so here you can see things that we do. Hydroxyurea has been given to quote fetal hemoglobin is something that even though it's not necessarily desirable to have, but for sickle cell folks it is. It's a chemical that can utilize it. There have been we're doing a lot more. Bone marrow works better when people have had cancers and treatment that have killed their bone marrow and getting bone marrow transplants. I do not know enough about stem cells, but it's clearly something we could use for that. And then, we're actually looking at things like gene therapy, trying to reprogram or using new stem cells in the body. There's research going on in this area. And in the interest of time, because I gave you a lot of information, we'll stop here. And I'll rejoin this when we start talking a little bit more generically about this. And just a quick intro. Globins are proteins. We can reuse those, break them down amino acids, use them again. Heme groups can. We can use the iron, but the heme group is a unique molecule that helps to hold oxygen that's got a base of iron. That we can't recycle. We have to break it down and excrete it. And very famously, it's going to be converted into something called bilirubin, and that can be a problem. And I'll leave you with this last word. What happens when livers don't work well, or there are blockages in gallbladders, or in where the gallbladder and the pancreas dump things into the duodenum, etc., and it's called jaundice. It used to be called yellow jaundice. And that has to do with this getting into the bloodstream. Enough said with that. We'll call it a dictation. I'm going to go watch the Super Bowl. So enjoy. I'll see everybody tomorrow and tell you all about this or whenever you listen to it. Bye bye.